I want to give you some intuition on using Taylor series to approximate a function. Let's pretend we have a car, and we'll give it a road to drive on. The car is going to have some speed, so let's include a speedometer. And we'll assume that it's initially traveling at 50 miles per hour. Let's call the current position of the car P of 0, and we'll put this under the front tire. Now we'll move the car forward in time. And where the car is located now, we'll call P of t. What I want you to think about is, can we come up with a way to express P of t? Here's one formula. It's P of t is equal to P naught plus the distance traveled. Since we're traveling at 50 miles per hour, and let's assume t is measured in hours, the distance traveled is 50 times t. We can use this to rewrite this equation as P of 0 plus 50 times t. But we're going to rewrite this again. Remember that P prime of t is the speed of the car at time t. Since the car is moving at constant speed 50 miles per hour, note that P prime of 0 is equal to 50. Now let's replace the 50 with P prime of 0. And we end up with this equation, P of t is equal to P of 0 plus P prime of 0 times t. When do you think this equation would fail? What assumptions were necessary about the speed of the car? This is what we'll talk about next. One thing we assumed in the previous example was that the car traveled at a constant speed of 50 miles per hour over the entire time interval. But in a real car, your speed may change. For example, maybe you travel 50 miles per hour for 4 seconds, and then 51 miles per hour for 7 seconds. Then our previous equation is incorrect. Let's see this with an example. Now we'll have two cars, and let's give them each their own speedometer. And initially, let's assume that each car is traveling 50 miles per hour. Let's call their starting position P of 0 in both cases. But I want the function P of t to be the position of the top car. So P of t corresponds to the position of the top car. Here's going to be the difference in the two cars. The bottom car will be like the previous example. It'll move at constant speed of 50 miles per hour. But the top car will have a speed that varies. It'll speed up a little bit over the time interval. Now let's assume some time passes so the cars move forward. The bottom car is the same as the previous example, so we know that its final position is given by P of 0 plus P prime of 0 times t, since it moved at constant speed. And now P of t represents the position of the top car, so let's include both of those pieces of information. I'm also going to include a line so that we can compare their ending positions. What I want you to get from this is that P of t is no longer equal to P of 0 plus P prime of 0 times t. But they are close to each other. Instead of writing equals, let's write the following. You should read this as P of t can be approximated by P of 0 plus P prime of 0 times t. And this squiggly mark means approximate. The reason they're no longer equal is because the top car underwent acceleration. If you wanted to make a better approximation for P of t, you could include a term to account for this acceleration, and you would end up with the following. P of t is approximately P of 0 plus P prime of 0 times t plus 1/2 P double prime of 0 times t squared. I hope these approximations look familiar to you. The first one is the first order Taylor approximation, and the next one is the second order Taylor approximation. Notice that both approximations are polynomials in this variable t. For completeness, I'll show you the formula for the nth order Taylor approximation. It takes the following form. This is actually the Taylor expansion, specifically around 0, but I don't want you memorizing this formula to be the takeaway from this video. I'm actually assuming you've already seen Taylor series before and have probably computed the Taylor series of some functions. Instead, I want you to think about the following. Taylor series can be used to approximate functions. For example, the position of a car can be approximated in terms of your starting position, your speed, and your acceleration. And as I pointed out at the end of the previous example, each Taylor approximation is a polynomial in t. Now let's combine these to get the following. Polynomials can be used to approximate functions. I want you to be open to this idea of using polynomials for approximations. The subject of the next video will be on approximated solutions to differential equations, and we'll be using polynomials as the approximations. This is where I'll end this video.